So let's remind ourselves over here that C has a parametrization given by R of t, where t ranges between A and B. All right? So how do we actually go about computing this guy? So remember what ds is. It's an infinitesimal arc length. And in the Riemann sum, it was given by this delta Si, which was the arc length of that little piece between, is it pi minus 1 and pi? Right? So how would we find the arc length of a piece of that curve? Well, remember, the arc length function is given by this, the integral from a to t of magnitude r prime of, let's call it tau for now, d tau. Okay? Well, we want ds, so let's take the derivative of this. So this is the differential I'm taking, actually. You might remember this from Calc 1. Right? So we take the derivative of what's here, right? And if you remember, this is just fundamental theorem of calculus. It says I take the t and I put it in where the tau is. Right? So r prime of t, and then dt, because I took the differential. Right? So if I just took ds dt, I would get just magnitude of r prime, but since I'm doing the differential ds, I get a dt over here. All right, well, so this tells me what ds is, and then I can essentially do like a change of variables in this integral here by plugging in r of t. So what that tells us is the following. It tells us that this integral here can be computed as the integral from a to b of f of r of t, right? So we restrict the function to the curve C, makes sense. And then ds becomes magnitude of r prime of t dt, right? So this here is really what we're after for computing these guys. This is how we will compute these sort of line integrals. And just a comment here, this is one type of line integral. This one here we'll call a scalar line integral. Right? This is just one of a few types of line integrals we'll study. All right? So hopefully that made sense, and now we'll do an example. All right, let's do an example now. So what we want to do is compute the line integral of f equals 18y cubed over this curve here, which is the piece of x equals y cubed from minus 1, 1, or minus 1, minus 1 to 1, 1. Right? So what does that curve look like? Right? So this curve, well, x equals y cubed is, it looks very similar to y equals x cubed, just goes the other way. Right? So it looks like this, the whole curve. Right? But we only want to go from negative 1, 1, which is here, negative 1, negative 1, up to 1, 1. Right? So really, we're going to get rid of everything outside of that piece. Right? So this here is C, this green curve. All right? All right, so what we need to do first is come up with a parametrization of this. Well, we have actually pretty conveniently one already here. So since x is given in terms of y, then we can just say, well, y is going to be t, and then that tells us x has to be t cubed. Right? So whenever we have equations where one variable is solved for in terms of the other, then it's pretty simple to find the curve. Right? And then now we have to decide on what is the domain of this. Well, if we want to end up down here, t has to be negative 1. And if we want to end up here, t has to be 1. Right? So what things do we need now? Well, we need the magnitude of the derivative, and then we need to plug that curve into the function f, right? And then that's what we're going to be integrating. So let's start by taking f of r of t, right? So it's 18y cubed. Here's the x, here's the y. So we're just going to end up with 18t cubed out of this. No big deal. Right, now we need the magnitude of the derivative of r. So first the derivative, 3t squared in t. The magnitude of that will be 9t to the fourth. Oops, sorry, this derivative should have a 1 here. Because the derivative of t is 1, not t. Anyway, plus 1, right? So now we can compute the line integral, right? So the line integral of f of xy over c, or along c, this is given by the integral from -1 to 1 of 18t cubed times the square root of 9t to the fourth plus 1 dt, right? Well, under the radical we have this t to the fourth plus 1, and outside we have this t cubed, so we can do a u sub here. So u is 9t to the fourth plus 1. du is 36t cubed dt, right? Well, this is exactly 1/2 of that, so what we get then is 1/2 square root of u du. But now what are the bounds? Well, if we plug in -1 to this, we get 10. And if we plug in 1 to that, we get 10. And, well, okay, so it's from 10 to 10, so this integral is 0, right? But that's how we do this, right? Now, again, we had this kind of thing before when we talked about double integrals and stuff. There is this idea of symmetry, right? Well, if you look here, this function, 18y cubed, is odd across the x-axis. And if you pick a point up here and you switch, say this is x comma y, and you switch it to x comma negative y, you're going to get the opposite value out of that function, right? And then since this function is actually, in a sense, symmetric, it's symmetric about the origin, really, but it's kind of, it has the same piece up here as it does down here, in some sense, in a way that's kind of behaves well with that function. So we kind of get the same positive and negative stuff integrating over this positive here and negative here, right? So you can see kind of from symmetry too, we should expect 0, all right? So hopefully that first example there of computing the line integral, at least this part, the symmetry can take some getting used to, but hopefully at least this part made sense, all right? See you in the next video.